She's an assistant professor in engineering physics at Wisconsin, and she'll be telling us about oscillating foil wake dynamics and predictive modeling.
All right, thank you so much for the introduction. Let's see, so I will start off by hopefully regaining control here, hold on. Okay, there we go. So I'll start off by talking about marine energy, which is the motivating background for a lot of this work. And then we will get into oscillating foil dynamics, and then multiple foils, and what we've been doing most recently, which is applying machine learning tools to this problem. So to start off, marine energy is a growing sector of renewable energy in the US, and the Department of Energy has divided this up into 4 categories. Energy from currents, so that's a steady free stream, either from a tidal flow or offshore ocean currents or rivers. Power from waves, which is an oscillatory displacement at the surface of the water. Ocean thermal energy conversion, and salinity. So what I'm going to talk about today is the first bucket here, or energy from currents. So the overall trajectory of marine energy is lagging that of other renewables, such as wind or solar, which is exciting if you're a researcher, because you can be in on some of the early research and development. But we also don't see a lot of these devices day to day, like we do solar panels and wind energy. And some of the reasons for this is that they operate in this harsh marine environment where deployment and maintenance and regulatory challenges have been some of the hurdles. So I guess this is an up and coming research area that is going to, in the future, hopefully be complementary to some of the resources, the other renewable resources we have. So where do we find these resources? In the US, the Department of Energy has mapped out locations where you can find current energy and wave energy along the East Coast and the West Coast, and in addition, a lot of resources in Alaska. Worldwide, we see that there's a lot of resources in a variety of countries, and I just will note that Scotland and the UK and France have been traditionally leaders in this area in developing this type of technology. All right, so
is the potential a lot greater than for wind energy?
So the potential, it depends how you compute it. So it has its advantages in that the energy is reliable. It's driven by the phases of the moon for the tide, or very steady ocean currents. So it's more predictable than wind. And then I guess, so it holds a lot of potential, but those other factors such as deployment drive up the cost. So it just depends what metric you're looking at in terms of available energy versus cost of getting that energy. Okay, so I'm going to walk you through a couple different styles of turbines, and this is not necessarily unique to marine tidal or rivers, but the first type are the bread and butter horizontal axis or axial flow turbines. So these look a lot like the wind turbines that you'll see when you drive around the Midwest. They are rotating about an axis that's parallel to the free stream flow, but you can note that water is 1,000 times more dense than air. So these blades are going to be stubbier and shorter, and also have a lot more force acting on them than their counterparts in wind. So that drives a little bit of the design decisions, but still this style device has been the most popular, likely because it was borrowed from the wind energy design tools. And the Sabella turbine here that you see in the bottom is one of the first that have been successfully connected to the grid and generating power. The second device is a vertical axis or cross-flow turbine. So this device rotates about an axis that's perpendicular to the flow. So this has lots of advantages because those flow vectors could change their angle slightly, and this device would still be able to rotate. You don't have to have an active yaw mechanism to align itself with the flow. And in wind, you see these called VATs or vertical axis wind turbines, but in water, you can place these horizontally. And this helps spatial configuration. If you have a shallow canal or shallow river, you can lay these out or stack them more appropriately in water. The final style device is what I will focus on today, and this is an oscillating foil. So this functions very much like these other two turbines. So the water is driving the motion, and the motion is driving a generator to convert electricity. However, it doesn't rotate. So the oscillating motion has different dynamics and implications. For example, you don't have to worry about entanglement, and you also would have to design your generator, or you won't have a rotational motion driving your generator. So you will have to convert that oscillatory motion into a rotational motion for a traditional generator. So this type of device has been looked at in prototypes mostly. So an example is down below. And you can see that these large yellow tape, that looks like yellow tape is defining the blades, and then the rest of the machinery is this actuation arm, and this would be sunk to the bottom of the river.
Is that going to be moved completely passively, or are things going to be done to control it in any way?
No, there's different mechanisms by which you can make this work. So you can make it completely passive by just limiting the linkage or the motion that it can move up and down. You can also make it semi-passive, so you could control the pitch and let the heave be passive, or vice versa. So I will give you some examples of a completely passive system, and then I'll talk about how we implement that numerically as well, because you don't have to always make it completely passive. Okay. But for now, I think if you just think about it as the flow pushing the foil passively and it having limits on its pitch and its heave, that would be appropriate. And it's completely symmetric. So as the foil heaves in the upward direction, it has a positive angle of attack. So then you have a positive lift force and a positive velocity, and you're generating power on the upstroke. And when you get to the top, you'll have a pitch reversal. So your angle of attack relative to the flow will be negative, but your velocity will also be negative. So you'll have a downward force, a downward velocity, and you'll also generate positive power. So you have this dual cycle. Every time you go from top to bottom, you have two cycles of power generated from this vertical force. And you can think about also getting power from that pitching moment on the pitch reversal at the top and bottom of the stroke. So if your moment is the same direction as your angular velocity, you can generate power from that as well. So this is another example. This is a prototype that of a team called Leading Edge that I was a part of at Brown University. So the video on the right is a GoPro of this foil flapping under the water. The left-hand side are the arms that are just holding the foil up, and then the foil are the somewhat elliptical shapes on the right-hand side. So this is completely passively driven. And if you look at the mechanisms on the left-hand side video here, the two arms are coded to stop at a specific location. And then the angle, the pitch angle, is mechanically linked to the heave motion, such that when the flow pushes it up, the linkages will push the foil downward. So that's how the completely passive system can operate. And then there's a sequence of gears to convert that linear motion into a rotational motion. I'll play that one more time.
So are you saying the pitch is set by the arm angle there.
Yep,
So
I
it's,
don't know.
okay.
There's like
So-
these little cables there that is connecting that pitch angle
Okay.
to the key.
So if you didn't do that, like if the pitch was totally free, like that axis that it's like could spin totally freely, it would pick like a lower resistance configuration probably. Is that right? Like it would be more streamlined with the flow.
Yeah, well, either, I guess it depends. If it's passive, it's going to be sitting on like a spring type system, right? So it would just maybe depend how much freedom
Okay.
to give it to pitch. I could think of a scenario where it would also rotate completely vertical as well, which would be not.
So you could use a spring to generate energy or something.
Yes, that's some of the semi-passive systems have that mechanism built in.
Okay.
Yep. All right, so this is a two-foil system. We quickly realized the benefit of two foils working together with one another, and our initial thought was that because our power cycle is cyclic, we could phase these two foils slightly out of phase with one another, such that while one is generating power, the other one is reversing its rotation, and that evens out our power stroke. But later on, we'll talk about how we could place these foils front to back and have even more benefits to these foils working cooperatively together. So first, just a few other features of these oscillating foils. So how efficient are they? If we compare them side by side with these axial flow turbines, their single device efficiency is about 30% hydrodynamically efficient, whereas the axial flow turbines are about 45%. But there's an argument to be made that even though the single device efficiency is lower, there's still lots of advantages. So if the efficiency calculation is the power that the device extracts divided by the power available in the swept area. So if I have a circular turbine, no matter how hard I try, I'm always going to sweep the same exact area. However, if you have an oscillating foil, in theory, you could change your heave amplitude and you could be sweeping a larger area. So that denominator becomes a moving target. So traditional efficiency might not always be your best metric for comparing these two systems. So that's my first argument. And my second argument is because these foils have a rectangular swept area, you can stack them next to each other and not have as much unused space between the turbines. So your energy, the potential to extract energy over a very limited area that you would have in maybe a river or a tidal flow might be, you might have some advantages to this size, to this shape and size of swept area. And then the third, oh, go ahead.
Is the area based on the total excursion of the wing as it flaps up and down?
Yes, by definition, the power denominator is that entire swept area.
Okay, and you're saying you could modulate that for the wing by making it have a larger flapping amplitude or something.
Right, which you can't do for a traditional turbine. If you rescaled it by, say, the chord length of the turbine, you would get a different metric. Instead of an efficiency, you would get like a non-dimensional power. And that would be a different metric to compare against. So it just depends which definition you are trying to optimize. And then the third point I want to make is that the fluid dynamics behind these oscillating structures are far different than something that's rotating. And that's what I will talk about at the second half of this talk. So the vortices that are formed from this foil develop into a structured pattern. And there's a lot of potential to, if you could predict what this structure looks like, you could have a coordinated array of foils that are taking advantage of these structures. The analogy to this would be, for example, fish schooling or birds flocking and taking advantage of the unsteady dynamics of the birds and fish in front of them. Okay, so in this next part, that made a lot of noise, sorry. Let's see, I'm going to play it really quick and then I'll turn it off. Hold on. There it goes. All right, so the way that we've analyzed these systems is by doing a combination of flume water tests and simulations. And so the flume tests are performed at Brown University by my colleague, Kenny Breuer. And in this example, you can see the foil is turned on its side, and we can actuate the precise heave and pitch and kinematics of that foil and record the forces on it. So in this example, we are not passively moving the foil, but we are actively prescribing the kinematics. But the resulting forces and power that we get from it would be equivalent to a passive system going through the same kinematic stroke. And we can do the same thing in the simulation. So we can prescribe the motion of this foil, and we can vary your heave amplitude, the pitch amplitude, and then compute the forces in order to compute the total power generation throughout the cycle. So this is just a reminder of what regime we are looking at here. So as you oscillate these foils, if you start flapping very quickly, you would generate thrust, and you will have a propulsor in the same way that fish or marine mammals propel themselves through the water. For these oscillating foils, though, they are not thrust generating, they are drag generating. So as we oscillate up and down, there is a large drag force on these foils, but there's also a large lift force on these foils. So the two come hand in hand, and that lift force is what we want to generate in order to create power. So although the motion looks similar, we're operating in this very different regime from propulsive foils. So some of the details on the simulation side. So we have a few different codes that we have run in these foil simulations. A lot of it has started off at Reynolds number of 1000, where we can easily change the kinematics and explore a very wide parameter space. And then we have also tested these foils at higher Reynolds number of 50,000 to match the Reynolds number of the flume experiments. And for that, we use large eddy simulations, which are 3D simulations, but periodic in the span-wise direction. And the way we have been prescribing the motion is through a dynamic mesh. So a dynamic mesh, in the dynamic mesh, we can prescribe the boundary condition of the mesh motion on the foil, and then solve for the displacement of each cell in the computational domain. So in this manner, we're solving our traditional fluids Navier-Stokes equations in addition to this mesh motion equation on the bottom right at every time step. This method, in order using mesh motion, enables us to put multiple foils in the same simulation as well. So you can imagine multiple foils with various kinematics deforming the mesh. We also try to push the mesh motion away from the actual boundary layer or the close, the near flow of the foil, such that the mesh distortion is not in a regime that's extremely sensitive to resolution. All right, so here's some examples of the simulation. So here we're looking at the span-wise vorticity and the pressure field. So what I want to emphasize here first is you can see the stroke is symmetric. So as the foil moves down, you have a red vortex, and as the foil moves up, you have a blue vortex forming. And these vortices on each half stroke is called a leading edge vortex. And these leading edge vortices correspond with a low pressure region. And that low pressure region is giving us an extra boost in lift. And if you look at the power as a function of the half stroke here, so again, because it's symmetric, I'm just showing the upstroke. You can see that most of the power in the blue line is generated from this heaving motion, right? So the lift force times the velocity. And if you compare different kinematics, you'll see that the most efficient foils are really taking advantage of this leading edge vortex. You can also see that the pitch power for many of the choices of kinematics that are optimal really does not generate much power at all. It gives us a little bit of positive power and then negative power, and is not producing that much useful power.
Is this video an example of a pretty efficient choice of pitching, amplitude, and phase? And
yeah, I think that's my next slide.
Oh, okay.
Perfect. So in this slide, we're looking at a wide range of non-dimensional. We have two examples of non-dimensional frequency. So reduced frequency by the chord length in the free stream of 0.1 and 0.15 on the left and right. And then we're looking at various pitch angles along the x-axis and various heave amplitudes for the different colors. And this is showing results across the 1000, Reynolds number 1000 DNS, Reynolds number 50,000 LES, and the experiments in the flume. So if you kind of just circled the most efficient of these kinematics, you'll see that there is a quite wide range of kinematics that give you these peak efficiencies. So those numbers are down below on the slide here. So this is good if you're designing a device. You have a range of parameters that you can generate energy in. You don't have to hit one specific narrow regime. And you're also seeing that there's not much variability between the low Reynolds number simulations and the higher Reynolds number simulations and experiments. So not only are we showing an excellent match, we're showing an excellent match across this Reynolds number regime. So if we look a little bit closer at that Reynolds number dependence, on the left, we have experiments, large eddy simulations, and DNS. And we've also changed the foil shape between the experiments and the simulations. So the experiments are at a different Reynolds number and also have a sharp edge or blunt flat plate compared to the ellipse cross-sectional shape from the simulations. So looking at the flow fields at the middle of the power stroke, so that's kind of halfway up the upstroke, and then at the flow reversal, the vortex formation is fairly similar. So you have a more coherent and stronger vortex as Reynolds number increases, but the overall pattern and dynamics are very, very similar. This was at first surprising to us, but then we realized that because we are pitching so quickly, our flow almost always separates at the leading edge purposefully. We want it to separate at the leading edge. We want to develop this leading edge vortex. So the traditional metrics of having a turbulent boundary layer versus laminar boundary layer are relatively inconsequential because of that inertial forcing of the boundary layer separation. So because we're always operating in this unsteady, unattached regime, our Reynolds number is quite insensitive. Again, we see some minor differences in power, but nothing dramatic. So this was great because this tells us that we can use the low Reynolds number simulations as predictive models for some of these higher Reynolds number experiments and systems. So if you look at the vortex dynamics a little bit more carefully, we can characterize the strength of these vortices. And the way that we did this, because we have three kinematic parameters, the frequency, the heave amplitude, and the pitch amplitude. On the upper right, we've calculated a relative angle of attack of the foil. So the relative angle of attack is the angle of attack the foil sees at a specific point. So we picked this maximum power generation point. So that's halfway up the heave stroke. What is the relative angle of attack? And we use that as a characteristic of the specific simulation or experiment. So again, we're changing frequency, heave, and pitch across a wide regime. And then we're just calculating this alpha T over 4 and plotting how the vortex changes in these different regimes. So by using this alpha T over 4, we could see that the max vortex strength correlates very well with this kinematic parameter. And we qualitatively, we can look at the images in these across this alpha T over 4 scale and divide it up into 3 regions. So the shear layer regime is where this leading edge vortex doesn't get a chance to fully develop. And that's the blue markers on the far left. And the red is the LEV regime. So here we have a coherent LEV, it's pinching off, giving us that lift enhancement we're looking for. And in the far right, we have an LEV plus TEV regime. So in this regime, not only do we have an LEV that's pinching off coherently, but the vorticity from the opposite side of the foil is rolling up into a trailing edge vortex and pinching off as a pair, an LEV and TEV pair. If you look at the efficiency of the foil across these 3 regimes, no surprise that the shear layer is giving us low efficiency. And then as you venture higher into this LEV regime and LEV and TEV regime, we're operating in this optimal efficiency region. And again, we are just seeing relatively consistent comparisons across CFD and the experiments.
So maybe you're going to say something about this, but why is there's a big difference between the black and the red in the max vortex strength, but a smaller difference in the efficiency? Is there a simple explanation for that?
So I think a lot of the difference between the LEV and the TEV is what happens downstream of the foil, because the LEV has only so much time to develop during that stroke. And that pinch off process happens a little bit towards the end. So you've kind of saturated that vortex growth during this red LEV regime.
Yeah.
And then the black regime is like the super saturated region, but it does have implications when we start looking at the wake structure downstream of the foil. So I do think it is a clear.
So the efficiency is basically like the lift force times the velocity divided by the power of the free stream, which is the same for all these different angles of attack. Is that right?
So, yes, you're correct. Except the swept area is going to change each time you change your heave amplitude or angle of attack. So okay. that denominator depends on your stroke.
Okay, so it's not just the lift force that's changing a lot, it's also the swept area.
Right, so you're changing the numerator and denominator on each time.
Okay.
Okay, well, those were great questions to lead us into this third part, where we start looking at multiple foils. So as the previous slide preluded to, the structure of those vortices as they leave the foil are going to form wake patterns. which you could think of as influencing a downstream foil. So the wake patterns that are developed are going to depend on those kinematics, right? How high have I pitched it? What's my angle of attack? Which one of those 3 colored regimes am I in? And then the second foil, its performance is going to depend on how it interacts with those vortex wake structures. So qualitatively, you can imagine it can have constructive interactions or destructive interactions depending on the timing and the location by which it hits these vortices. So here's some examples. On the far left is our bread and butter rotational axis axial flow turbine with an efficiency of 45%. And in the middle, we have what's called a tandem configuration. So these are 2 foils that are completely front and back from one another. So they are taking up the same swept area, right? So they're sweeping the same area. So the denominator, that YP value, stays the same. And you can just add the efficiencies of those 2 foils to get a system efficiency. So this tells us, based on these simulations, that our system efficiency could be about 40%, which is already approaching 45% of our rotational system. On the other hand, we can imagine a staggered configuration. So in a staggered configuration, the second foil now sees fresh flow, right? It's no longer completely in the wake of the first foil. However, now we've doubled our swept area. So the swept area is much larger. So when we compute the efficiency, we really are taking the average between those 2 foils. However, what we've seen is that in both these systems, especially in the second system, that eta 2, or the efficiency of the second foil, is actually depending how you time these, can be more than eta 1. So you can see some constructive interactions. And likewise, in the tandem configuration, these foils are mostly governed by negative or destructive interactions. So this was very motivating to us. And another example to kind of motivate what we're going to look at is, this 4 foil system. So these tiny little blips there are foils, and you're looking at you're zooming out and looking at the wake, and the flow is actually inclined at an angle of 15 degrees. And the numbers that we're looking at is the percentage of power that these 4 foils can produce as a percentage of a single foil by itself. So the first foil is getting 98% there. To what you would have at a single foil at 0 angle of attack. The second foil is 84%, but the third foil is producing 1.11 times more power than the single foil. So it's definitely benefiting from some constructive interactions. So all of these numbers change depending on the phase, the position, and the timing of these foils and how they are sweeping through the flow. So I guess this is motivating and interesting, but it's also a very large parameter space to explore.
Is this from a simulation?
Yes.
So you covered this whole space with finite elements or something? Or?
Yeah, so that it's through the dynamic meshing. So each one of these foils is moving the mesh, and then we're just recomputing the location of those new points. So
these simulations must take a long time.
Yeah, it's still 2-dimensional, so it's not too bad. This is a 2D simulation at Reynolds number 1000, so it's not that bad.
So you chose beta to be 15 degrees. Was that sort of arbitrary?
We actually swept from 0 to 45 degrees, and 15 gave us the best total power. So We did change that parameter. We did not change the actual kinematics of the foils. So we kept that the same. And we didn't change the spacing of the foils.
Can I ask about the spacing of the foils for a second? Because it would seem like you might want to normalize by, I guess, the spacing that you would require for the radial foils. Is that intuition reasonable?
I guess if you wanted to compare directly with those systems, that might make sense. The spacing here is, I think this is about 6 chord lengths in the X direction, maybe 6 chord lengths as well in the Y direction. So this is kind of the regime that we've settled on in terms of being close enough where we're seeing an interaction between the two foils, but not so close together. So we played a little bit around with that parameter, but we seem to have settled into this 6 chord length separation area. I don't know. I'm happy to talk about that more later.
Sure. Thanks.
Yeah. Actually, that leads in nicely to this next slide. So the data that I'm going to show next is talking about a simpler system of just 2 foils, and the SX is the distance between the foils. And in this system, to reduce the parameter space, we're flapping both foils at the same frequency, heave, and pitch amplitudes, but we're changing the phase angle between them. So the phase angle of 0 means that they are doing the same thing at the same time, or completely out of phase means that one is at the top of its upstroke and the bottom of its downstroke. So the distance can change and the phase angle can change, but the 2 foils will do the same kinematics. And then we can cycle through all of those kinematics that we did before. And we can look at what is the best system efficiency that we get for each one of these kinematics. So again, we're changing that alpha T parameter, and we're taking the efficiency of the system. And this just confirms that we are seeing an efficient system working together over the same wide range of kinematics that we saw before. So over the LEV regime and the LEV plus TEV regime. And if you look more carefully, we can see, so each of these dots I have on the plot is taking the optimal phase angle. So this is the best case scenario when the 2 foils are phased phased at the optimal phase angle. And we can just see how these vortices qualitatively are interacting with the downstream foil. And our observation is that in order to have this best case scenario, that second foil is avoiding the strongest vortices and trying to stay completely out of phase with the wake in front of it. So any interactions that are happening with the vortex and the foil are destructive in this configuration. So we went a little bit further, and our motivation here is we wanted to be able to characterize what the wake looked like in order to better predict how that second foil will perform. So to characterize it, we did 2 things. We said, well, let's look at the mean wake. So we sampled the wake downstream, and we found that the wake deficit scales with that alpha T/4 variable, which makes sense because the more energy we are extracting from the flow, the less available kinetic energy there will be downstream. So the bigger the wake deficit. So that alpha T/4 has a much stronger wake deficit than at higher alpha T/4 than lower alpha T/4. And then we also found that, and so this scaling, this UP variable is like a mean convective wake in between the 2 foils. And so that decreases as alpha increases. And we also found that there is a negative wake deficit on the fringes. So at the very top and bottom in this green region on the plot. And this green region is primarily where the LEV travels through the wake. So we could characterize the unsteadiness of the wake by looking at the fluctuations with respect to the mean. And we can see that these fluctuating values are indeed occurring at the path of the strongest vortices of these LEVs. So that gives us a sense, a qualitative sense of what these wake structures look like as a function of these different regimes. And you can see that this unsteadiness increases significantly as alpha increases. So the higher alpha gets, the more unsteady the wake becomes. But again, the unsteadiness is being pushed to the top and bottom of the wake. So in order to predict the performance of the second foil, just to give you a sense of this huge parameter space, the slide is very busy, so I'll try to walk you through. So once we know what the wake looks like, we can say, well, the efficiency of the second foil is on the x-axis. And this phase angle of how the two foils are phased with respect to one another is on the x-axis. And then we can rescale this phase angle as a function of this mean convective wake velocity, the frequency at which the foil is flapping and the distance between the two foils. So by doing this, we can collapse this data a little bit into what's called a wake phase. So the right-hand side has this wake phase parameter, and it's capturing kind of the maximum and minimum wake phase that you can have in order to get the optimal efficiency for your second foil. Okay, so this was a great finding. However, it's not capturing everything. So
sorry.
Go ahead.
So the wake phase is like saying the vortices from upstream foils are hitting the downstream foil at the same phase, kind of. That's sort of what it's capturing, is like the timing between the downstream foil and the vortices from the upstream foil, something.
Yeah, you're rescaling it based on this convective speed, but also the flapping speed. So it's kind of like the spatial wavelength of that vortex wake, and how that second foil can stay completely out of phase with that non-dimensional spatial frequency.
Okay.
Right. So if you look at this across the three different regimes, our shear layer regime, our LEV regime, and our LEV plus TEV regime, we found it did very well in our LEV regime and not so well on the other two ends of the spectra. We're not so much worried about the shear layer regime because this is a very low power generating regime, but regime C, our hypothesis here is that we are missing the impingement of the vortices on the second foil. So we're capturing the mean flow and how we're kind of staying out of the way of the bulk of these the trail, or kind of staying out of phase with this trail or this wavelength. But there's still many more vortices in the flow that are interacting with the second foil, and we're really not capturing this. So one of our current goals is to revise this and account for these extra interactions that are destructively affecting the second foil. All right, so here's some examples. The left-hand side, you can see one phase angle of 240 degrees, and you can watch that second foil kind of successfully circumvent what is happening. And the line below has the power from foil 1 and then the power from foil 2 renormalized with respect to this mean wake. So basically, if you give it a new denominator based on this mean convective velocity, foil 2 can equal the power generation of foil 1. However, if you change the phase on the right-hand side, when the phase angle is equal to 90 degrees, now foil 2 is destructively interacting with the vortices, and its relative power with respect to foil 1 has decreased. So this is an example of these discrete vortex foil interactions. If you think about sweeping through all of these phase angles, you can watch this evolution. And sometimes the red line goes slightly above the blue line, but for the most part, it will stay equal or less than the blue line. So you are seeing these destructive interactions.
So colliding with those vortices from the upstream foil is generally not a good thing.
Yes,
Okay.
correct. In this configuration, although sometimes you see like slight benefits, but this tandem configuration, we're seeing mostly destructive interactions.
But I mean, there are other experiments where people see constructive interactions where
Yeah.
like the vortex from the second foil kind of merges with the one from the first foil. But so you could set your system to do something like that, but I guess
Yeah.
you don't
Yeah.
really see that.
You're absolutely right. So if you, I can show that here. If you imagine this system is a tandem configuration, so we're forcing the second foil to be directly behind in the same swept area as the first. If you stagger it, so if the first foil is allowed to go slightly above the first foil in terms of its swept area, it is then in a position that it can grab those vortices and use them constructively.
Okay.
But due to the configuration of this system, this is the limitations that we're seeing. What we hope is that by looking at the differences between these two power curves, we think this is a good model for the unsteady contributions to the power extraction. So we think this yellow region, the area between the two curves, is capturing these vortex foil interactions. And we hope that, by continuing to explore this, we could characterize these interactions and then apply it to other configurations where it might be inverse, right? Where the second foil is getting more power than the first foil. But this is based on the data set we have. These are our conclusions thus far. This is the same video. Okay, so the last part of this talk, I wanted to talk about how we are applying some machine learning to learn more about the wake structures that emanate from the foil. So what you're looking at here is 6 different images of the wake between the two foils. So you can imagine the first foil is on the left-hand side of the image and the second foil is on the right-hand side of the image. And we're just taking these wake structures in between. And what we wanted to do is we wanted to find a way to automatically classify and cluster these wake structures and see if machine learning could elucidate some new findings into how these wakes are organized that we couldn't find on our own. So we're looking at very similar data sets to what I had already shown you. So you can imagine we have all of these 46 different simulations. Each simulation is flapping the foil at a different frequency, heave, and pitch amplitude. And then we take samples of the vorticity field, 200 or 300 images per simulation. We interpolate them onto a 128 by 128 Cartesian grid, and we're looking at discrete levels of vorticity. So we've chosen to use vorticity, an image-based process, in order to characterize these wakes. So I will just point that out for a bit. Instead of using a point-based method, we've decided to keep this method image-based. But then, of course, the algorithm just looks at a matrix, right? So it's just looking at a matrix of RGB values based on this vorticity field. So the first neural network that we did is a classification network. So in this case, we tell the neural network, we have 3 classes of flows, and we use those same 3 regimes from the previous section, regime A, regime B, regime C, and we drew lines at alpha t/4 at specific values, and we trained the algorithm to sort the stack of images into one of these 3 bins. So the neural network is embedded with LSTM units, so long short-term memory units. And this maintains a bit of time dependence. So it actually gets a sequence of images, sequence of 5 images, so that it can also track the trajectory of the vortex and not just a still image. So here's an example of the classification model architecture. So again, that input is the samples arranged in blocks of 5. And then after it goes through the various convolution layers and the LSTM layer, the output is sorting it into one or classifying it into one of these 3 categories. So the results of this were fairly successful. If you start by looking at the top right, this is an example. We used a 5-fold stratified cross-validation, which basically means stochastically we're doing this 5 different times with different groupings of samples. If you want to have 100% across the diagonal, where your predicted and your actual pre-labeled for each image aligns with one another, and the orange, the red, and the pink are areas where they did not align. And if we expand this data further, and if we say which images were not being classified correctly, we're seeing the orange and the pink are primarily at the edges of these bends. So the stuff it's getting wrong are the ones that are close to the other classes. So this was useful, and you know that the algorithm was detecting something in the wake images that we had preliminarily decided these classifications based on just the strength of the LEV. So when we first decided on these lines, we weren't looking at the wake images, we were just looking at the LEV on the foil itself. So the second thing we wanted to try is we wanted to see if the neural network can automatically determine these groups. So this would be clustering instead of classification. So
sorry to interrupt, Jen. Normally we'll end in like a couple more minutes. So I just
sure, I'll wrap up.
Okay.
Yeah. I can go through this quickly. So in this case, we had an autoencoder that can decode these images into a latent space. And inside this latent space, it will cluster the images independently. So again, we start with 11,000 images across all of these kinematics. Each are sorted separately into various clusters. And this slide just says that you have to determine the number of clusters, and that's the only thing you give the algorithm. So this is telling us that we want somewhere around 4 to 5 clusters. And the results are shown here, where 4 clusters are determined automatically by the algorithm. And these clusters happen to be very close to what we originally had for our classification and our previous 3 regimes, with the exception that we have drawn an extra line through the middle regime. So finally, we wanted to see what was it in these wake images that the machine learning was picking up. And by randomly sampling a few of these images, we can see that we think it's the wavelength of the structure that is our hypothesis, that the algorithm is detecting, and also these LEV TEV vortex pair in the 4th row below. Finally, we were interested to see if the algorithm would find the difference between these upper branch and lower branch in regime D. And no matter how hard we tried, we couldn't get it to sort the difference between those two. We know the answer. The answer is that those 2 branches have different frequencies associated with them, but it was not something that the algorithm was able to pick up. All right, so that's essentially it. This slide is just going into more detail about the unsteadiness and linking that back to the neural network and machine learning portions. And we think combining those two could be very fruitful. And I will stop there and see if there's any time for questions.
Okay, thanks a lot, Jenny.
We have a question in the chat. Can we use a dam or tidal fence type structure rather than turbine?
Yeah, so a dam operates on a different principle. So that's storing potential energy rather than using the kinetic energy from the free stream flow, if that's kind of the question. So in this research, we are interested in really capturing the energy from moving flow, not potential energy.
So what about the tidal fence? I'm not actually sure what that is, but I guess it's somehow stopping a steady stream going past it.
Yeah, I believe that's right. I believe you are, as the flow comes in, you capture it and then release it, if I'm understanding that correctly.
So that's just a different strategy, I guess.
Yeah, so it's a different way of converting energy. So you're going from kinetic energy to potential energy and then storing the energy as potential energy. So that's traditional hydropower. And so traditional hydropower has its advantages, but it's there's very little places for adding new traditional hydropower. We've kind of, at least in the US, we've utilized most of the rivers already for that purpose.
There are questions?
Yeah, there's another one in the chat. Are there any considerations on how wake profiles would affect marine environments, especially in shallow areas?
Yes, absolutely. There's many people concerned with the effects of flora and fauna of these turbines. So there's different experiments that are being done. My takeaway from all of those experiments is that it's very much, it's very specific to the location. So migratory animals, for example, are going to be different no matter what river or what microenvironment you're in. So there's really, determining the effects has really been a case-by-case study in different locations.
Other questions?
Can I ask again about the spacing between the foils?
Sure.
So how, just as a preliminary, I guess, how do people construct arrays of multiple circular arrays, circular turbines? Is that done?
So the traditional cross flow or the traditional axial flow turbines,
Right.
yes. And so the traditional approach to that would be to wait until the weight completely recovers.
Correct.
So you want to get that recovery distance, and that's about, maybe 10 turbine diameters downstream. So that's it, and it's more complex than that, right? Because you can stagger them and you can have different configurations where they're not just back to back. But that's the current working philosophy for developers.
I see.
Nice talk, Jen. I just had a related question. So, presumably this becomes really complex once you have multiple objects, or maybe you go to 3D, like computationally, this becomes extremely challenging, right? In your future work, like what makes it more challenging? Like, are you looking at like multiple, or are you looking at like moving to 3D, or?
Yeah, 3D, we are not so much interested in 3D because the long slender blades give us relatively a two-dimensional flow. So even if we go to 3D, it's kind of to increase the Reynolds number and do a three-dimensional large eddy simulation, but we're not interested in like tip effects on the blade, for example. That's something that, we could put end plates on and mitigate.
You think the wake becomes inherently 3D though?
So that's something we have looked at. We've looked at that in the flume as well as in our LES to see what kind of, three-dimensional instabilities might exist as the Reynolds number increases. And so far, at least at the Reynolds number that we stayed in the Reynolds number regime of about 50,000 and done careful comparisons against the Flume results and the simulations. And you don't see a big difference in terms of like those LEVs convecting and the basic structure of the wake. They're very similar. So there might be, perturbations, three-dimensional perturbations changing the vortex dynamics, but they're not having a huge bulk effect on the wake or the trajectory of the vortex. So that was our conclusion from going from 2D to 3D. But back to your question, I think what we would like to do is we would like to develop a model for predicting the vortex interacting with the foil and then extrapolating that to many foils and being able to have a model for what configurations and kinematics, how we can optimize that parameter space.
But why extrapolate though? Why not just simulate the multiple?
Yeah, it's just the parameter space is so big because you can change the configuration and then you have to sweep through all the different kinematics and so you could keep the kinematics the same and just change the spacing. I mean, it's a very large parameter space.
Thanks.
So sorry, I guess, are you trying to get a reduced order model or something, or just not think about such a large parameter space?
I think what we would like to do is to be able to have a reduced order model for that vortex blade interaction and then combine that with or utilize a neural network to give us kind of a predictive capability to say, we want the foil to circumvent the wake, or we want the foil to interact with the wake at this timing. And then we would be able to use the reduced order model to compute the lift benefit or the delta CL one way or the other, or the delta power.
Does somebody else want to ask a question? So I've seen more work about like generating propulsive forces from flapping foils, not so much about the extracting energy with flapping foils. So it's really interesting to see what the fluid mechanisms are here. So I guess, so a lot of the power you're getting is from lift forces, right?
Yeah.
So when you have just a single foil, if you make the angle of attack, you increase the angle of attack and the lift keeps going up until you get to the stall angle. And then the lift drops and the drag goes up. So here, though, it looks like you want to get to very large angles of attack. So the lift, I guess, because it's unsteady, you actually get larger lift with these kinds of unsteady stall types of flows.
Yeah, you can think about it as you're pitching up so quickly that you're stalling it immediately. And then you develop a stall vortex, but then you flip it over before that stall vortex has shed.
Okay.
So you're timing it such that you're taking advantage of the stall vortex just at the right time. You flip it over and repeat.
How much better do you think that is, like some of the best things that you found compared to if you took just a foil and you brought it to the stall angle? So that's kind of where the maximum of the lift curve is for a steady airfoil flow. And then you just kind of kept it at that for a while, and then you flipped it back the other way, which is a little bit like a sail on a sailboat, I guess. They kind of like so
you would say you're trying to keep the flow attached the whole time.
Yes, exactly.
Yeah.
Maximize the lift, but keep the flow attached. And then when you get to the maximum of your excursion, just go back the other way. And I wonder, like, how much power would that get compared to what you've got here? I wonder.
But you can generate power that way, but your efficiency will be about 10%.
Oh, okay. So people have looked at that case.
Yeah. Yeah. You're generating power. You're just not generating as much power. Yeah.
Okay. And then I also wonder, like what you showed here, you let this alpha T/4 go up to around 1. But I could imagine there's still a much larger space of kinematics where you could let the foil flip over, or it could also have an upstream downstream oscillation, or there could be sort of arbitrary 2D motions.
Yeah.
Have people looked at like that, like more general space of things?
People have looked at like non-sinusoidal strokes, so periodic, but like a trapezoidal stroke. So you can get some benefits that way. Nothing too dramatic. You can also, I'm pitching about the center. You don't, if you have, an airfoil, you could pitch about the quarter chord. So all those will give you like slight differences in the stroke and the kinematics. But you're not going to be boosting your efficiency. You're not going to be doubling your efficiency. It's just small boosts. But yeah, they all have, and they all will have the same trademark, LEV formation, just slightly different.
So you don't think there's some totally different type of motion that might do better in efficiency?
Yeah, I haven't looked at something flipping all the way over. I've considered it, but we haven't done that.
Right. Yeah, because since the unsteady effects are so important here, you could really get very different vortex formations if you had it flip over or do other things. So I don't know.
Yeah, it could be cool.
Yeah. All right. Well, thanks a lot. That was really interesting.